You have a double bond, and then you're using the double bond to make a nucleus. So what you should have to think about is, this can be done by something called carboxymercury and demercury. You get the mercury ion added to double bonds. And then that base is an asymmetric, meaning that you use more electron there, more substitute side. Using a methanol, because we have a methoxy group there, methanol making a tag there, opens it up. So that is how you open it up. And then the mercury, you get rid of it by adding sodium borohydride. So you get that. You have to convert alcohol to the ether, right? So what you do, you take the protons off by the sodium hydride or the sodium metal, depending on what you want. And then that takes the proton off, making alkoxide, right? O minus. That's a good nucleophile. If you have a halide there, you get that SN2 reaction done, and you can prepare ether. This, you just have to be very, very careful. Because of that reacts with alcohol, and then what it does is it get the hydrogen gas coming out. So this H minus. I mean, either way, this one or that one, you get hydrogen become hydrogen gas, it comes out, and then it generates a heat. So if you heat up the hydrogen gas with the oxygens in the lab, it can explode. And then you can get the fire. And the funny thing is, about 2 weeks ago, my lab hit the fire because of that reason. So we had to get the big fuel came in and then cleaned up, inspected it, worked through a lot of regulation problems. But anyway, that's why organic chemistry. If you do organic lab, you gotta know what you're doing. Otherwise, you can end up having trouble. Yeah. Anyway, the thing is, the organic chemistry uses a lot of reactive chemicals. The thing is, if it's a stable chemical, they're never going to go through the reaction. Then you cannot do chemistry. So that's kind of the nature of the chemistry. We always work with dangerous chemicals. That's how we make new stuff. So you have to respect the new chemicals, and you got to know what you're doing. So you got to do a lot of MSST searches, and then know the safety issues and how to handle those things, how to dispose them. Yeah. Otherwise, you can get into trouble. I always told people that working in organic lab is like you planted a fire at the gas station. That's how it is. I mean, seriously, I got a couple of fires in my laboratories. Thankfully, nothing happened. But you've seen the photo. Anything happen? I've seen the neighbors' labs that incinerated overnight. And, it's dangerous. But that's why you got to know what to do. That's why your lab TAs are keeping your heart. Well, some are justifying their efforts. But anyway, these questions are open epoxide. You can see that epoxide is there, right? This is a single substituted site. That's a double substituted site. You gotta be careful about those asymmetric epoxide. How you what you really use it, you open it up. You got green yard, right? The green yard, you cannot use a proton with it. And we just talked about acidic proton will just kill the green yard. So this is a no protonation there. So the green yard is a strong nucleophile. Where the nucleophile is going to go? Is it going to go to the more substituted side, just like we've been talking about acidic catalyzed reactions? If you're nodding, then you really have to go back and study it, because that is not what nucleophile does. Nucleophiles are very sensitive of the substitutions, right? More substituted side, it never go there. So where does it go? It goes to less substituted side, opens it up. So where the phenyl groups end up being, less substituted side. And then this oxygen goes to more substituted side. So the position, where the thing's going to go, where the nucleophile is going to go, where the other side is going to get, that's what we're going to look at when we ask these questions. So you have to know the mechanism to solve it out. And the one down there, I know this is drawn very funny way, but the thing is, it's an acidic condition. You see there's a proton there. So what it means is, methanol, someone may think that, well, maybe methanol becomes a nucleophile. Why not this thing attacking this less substituted site opens it up? Why does it happen? If the methanol becomes a nucleophile, then it's going to attack the less substituted site and it opens it up. Why that doesn't happen? Once again, if you don't understand that, you got to go back to Chem 1. So the reason why is that methanol is a bad nucleophile, right? That's what we talked about. Neutral alcohol is a bad nucleophile. That's why if you drink a beer, if you drink a wine, you don't get that. You better enjoy it, right? It's because of those alcohol in the beverages, they're not killing you by making nucleophilic 10. There are these things are not nucleophilic. So they're not attacking, it's because it's not nucleophile. So that's why we need to motivate these groups to get open by the nucleophile, such a bad nucleophile. That's what protons are needed. Proton basically make the oxygen more electrodeficient. It motivates the oxygen to 2 electrodensity out of these 2 carbons, but it's going to lose more substitutory site, lose more electrodensity. Then stage is set. Big nucleophile like this. Now it can go attacking more substitutory site because that's the more efficiency there, and then opens it up. So you end up having nucleophile, nucleophilic alcohol, alkoxy groups sitting on the more substitutory side, then the less substitutory side getting weight, that the oxide oxygens are there. And then that's a regiochemistry.